With a slight modification of the technique that we learned earlier about using definite integrals to find the area under the curve, we can tackle a couple of important business applications. And the idea here is to learn how to find the area not just underneath the curve, but between two curves. And you can sort of see the picture here, what I mean. This turns out to be very simple, at least in theory. For example, in this figure, all we need to do to find that shaded area is to take the area under the lower curve, it's the part that I've boxed in red and labeled area under lower curve, and subtract it from the area under the top curve, which is the curve that's labeled F. The area under the curve F is everything between A and B under F, and if I take that area under the curve F, which we know from our study of definite integrals is just the integral of f of x from A to B, and then I subtract off the area under the lower curve, which again we know from our last discussion is just the integral under the lower curve, which is g from A to B. Take that the smaller quantity from the bigger quantity, and what that leaves me with is the area between the two curves, which is what I'm looking for. So it turns out that finding the area between two curves, at least in the simplest case, is very simple indeed. You just take the upper curve minus the lower curve and integrate between A and B. And of course that's true when you have the same curve on top throughout the interval from A to B. But in that simplest case, the procedure is really pretty trivial if the algebra is not bad, and sometimes if the arithmetic is not bad. So let's take this result and see if we can push it forward with some examples. But the bottom line is to find the area between two curves f and g when f is always on top in that interval and g is always on bottom. You subtract the two functions and integrate from A to B. About the simplest case I can come up with is when both the graph and the interval are given to you and there's one curve always on top over the interval you're interested in. And this is probably a perfect example of that. I'm using f of x equals 3 times 1/3 x squared, which is a parabola opening downward, passes through the point 0, 3, and g of x equals 1/3 x squared, that passes through 0, 0, and it's a parabola opening up, and the interval of interest is the area between 0 and 2 that you see shaded there. This satisfies the condition for finding the area between f and g, which says just take the difference between the two functions, integrate that from A to B. So in this case, again, top curve minus bottom curve. And in this case, we're interested from 0 to 2. Using the formula, f is 3 minus 1/3 x squared minus g, which is 1/3 x squared. And so you've got a minus 1/3 x squared minus another 1/3 x squared. So you end up in the integrand with 3 minus 2/3 x squared. We have to integrate term by term. We know that the integral of 3 is 3x. When we're integrating 2/3 x squared, we can just let the 2/3 sit there, and when we integrate x squared, we raise the 2 up to a 3, and then out front we divide by that 3. So we end up with 1/3 x cubed, and of course that 2/3 gets multiplied in there. You simplify that, 2 times 1 is 2, and 3 times 3 is 9. Quite often, the hardest part of any of these problems is either the algebra or the arithmetic, not the calculus. The calculus is relatively trivial. What do we do now? We evaluate. Remember, it's upper minus lower. So we plug in the upper limit, which is 2, minus what you get when you put in the lower limit. Well, luckily, the lower limit is 2, and when you plug in 0, you're going to get all zeros. So that makes the arithmetic a little bit easier. And remember, when they give you these problems, unless they tell you to approximate, they're not looking for a decimal approximation. They want the exact value. Practice this a little bit and you should find it very simple. How about this example? This time, you're given the two functions, but you're not given a graph. That presents a little bit of a challenge because when you had the graph in front of you, it was easy to see what was on top. So if they're not given to you at all, the graphs, then you've sort of got to get enough idea of a sketch of this thing to figure out which is on top. So luckily for us, these are both parabolas, and we know about parabolas, but we have to figure out in our mind at least which function is on top over the interval, or if they switch, we've got to know that too. So again, because we know these are parabolas, they're fairly simple to do. The parabola y equal x squared is the prototypical parabola. We know that its vertex is at 0, 0, and it opens upward, so it looks sort of like the graph I've sketched out there. You don't have to necessarily have a pinpoint accurate graph, but you've got to have a generally good idea of what it looks like. The second one has a negative x squared, and we know from algebra when the leading coefficient is negative, the parabola opens down. And if x is 0, y is 32, so you can sort of tell it's going to go through the point 0, 32. That'll be the vertex. So if you put those two things together with the regular prototypical parabola y equal x squared with the one that opens down and goes through 0, 32, you'll see that this is what they're asking for. And you can also see that what we need to know is where these two curves intersect, because that's going to determine our limits of integration. So the first thing we have to do when we don't already know it is to find the points of intersection. But that's easy. You just take the two curves and solve. So since y is equal to 32 minus x squared and y is equal to x squared, I can just plug x squared from the second equation into y for the first equation and solve. So if I take the x squared to the left-hand side, I'll get x squared plus x squared, which is 2x squared equal 32, and then divide by 2. That means x squared is equal to 16, which means x is plus or minus 4, and bingo, I have those points of intersection. So some pretty easy algebra will give you those intersection points. So now we're ready to integrate, because we can see that one curve is always on top between minus 4 and 4, and that happens to be the curve y equal 32 minus x squared. So we should be able to do this now, fairly straightforward. Bounded area, that shaded area, is top minus bottom between minus 4 and 4. It always has the same one on top, and in this case it happens to be the 32 minus x squared. So I take 32 minus x squared, which is the top one, minus x squared, which is the bottom one, and that becomes the integrand, and I'm integrating from minus 4 to 4. Well, that's pretty easy actually, because minus x squared minus another x squared is minus 2x squared, so the integrand just becomes 32 minus 2x squared. If you integrate 32, you get 32x, and when you integrate 2x squared, remember the 2 just sits there, and then you increase the power by 1, making it a 3, and then you divide by it. So you end up with minus 2/3 x cubed, and you're evaluating from minus 4 to 4. What I was about to say is at some point before you get too far into this problem, it would be nice to notice that there's symmetry as well. The part of the area you want to the left of 0 and the part to the right of 0 are the same. So you can use the symmetry. So rather than integrating from minus 4 to 4, I would actually just integrate from 0 to 4 and double it. That's what I would do. I would go from 0 to 4 instead of minus 4 to 4 and double the area. And I can see why that's going to be true, because that area and that area are the same. It just makes the arithmetic easier. If you notice that, the problem's easier to do. So what do when you integrate? You take the antiderivative, which you've already done, and you plug in the top number and then the bottom number and subtract the two. So when you plug 4 in, you'll get a 4 in place of the x there and a 4 in place of the x there. And when you plug a 0 in at the bottom, everything goes to 0. And so it actually is not bad at all. So what we're dealing with is 32 times 4 there. Well, 32 times 4 is 128. And here you get 4 cubed. And 4 cubed is 64. And then you've got to multiply that by 2. That gives you 128. So you end up with 128 thirds. So you've got 128 minus 128 thirds that has to be doubled. I would just leave the 2 alone right now and get a common denominator. Remember, 128 is like 128 over 1. So you have to get a common denominator. So you multiply by 3 over 3, and you end up with 384 thirds minus 128 thirds inside those brackets, still getting doubled in the end. 384 thirds minus 128 thirds is 256 thirds. And then when you multiply by 2, you'll end up with 512 thirds. And again, unless you're told to approximate, they want the exact area, which means you don't need to be rounding things off to a certain number of decimal places. You need to stick with the exact answer. In principle, this is all very simple. The calculus is especially simple. The main thing is practicing the algebra, and maybe for some of you, practicing the arithmetic. You don't want to do all the calculus right, all the algebra right, and then blow it on the arithmetic. So take time to practice these skills. Now, why did we do these things? Well, one of the reasons we did this was so we could discuss that business application that I talked about earlier. And I'm ready to do that now, and that'll wrap up this lesson. The two business applications that we're going to use the area between the curve technique on are consumer surplus and producer surplus. If you've taken an economics course, you probably have heard those terms before, but basically they come from this. If you've got a demand curve that describes the demand for a product, and you've got a supply curve that describes the supply of the product, wherever they intersect is called the equilibrium point. And economists have a name for that area in that figure that I have labeled called the consumer surplus that describes the area, the region that's below the demand curve. It's below the demand curve, but above the horizontal line that goes through P0. It's that area right there. That's called the consumer surplus. It's the difference between the amount consumers would be willing to pay and the actual amount paid for the product. And that's an economics term, and we're not going to go too much into that. I'll leave that for your economics professor. But we want to learn how to calculate it. And then this area shaded below the consumer surplus, this labeled producer surplus, it's that area right there. That's the area below the horizontal line P equals P sub 0, which is the y-coordinate of the equilibrium point, and the supply curve. That area is the producer surplus. And the producer surplus is just the difference between the amount a producer receives for selling a product and the minimum price needed to get the producer to supply the product. Again, not going to go into the details of the meaningfulness in terms of economics for all this. I'll leave that to your economics course, but simply how to do those calculations. And that's how we're going to end this lesson, is to do the calculations on an example. And remember, this x sub 0, y p sub 0 represents the equilibrium point. That's the x coordinate and the y or p coordinate of the point where the supply curve and the demand curve intersect. Now that formula, as we said, is that shaded area up top that's labeled consumer surplus, and what it is the difference between d of x, that's the top curve, that's on top, and the bottom curve, which is p sub 0, it's on bottom. So it's the top curve minus the bottom curve, just like we were doing earlier. Now, lucky for us, actually it's not so lucky because it's not hard either way, but when we get to the point where we're integrating just a number, remember p sub 0 is the equilibrium price. It's just a number. When you take the antiderivative of number, you just get the number times x. So you can actually go ahead and integrate this part of the formula and get a simpler formula. And this is the way I would remember the formula for the consumer surplus. You can just remember it like this, which is perfectly fine, but it's probably easier to realize that when you're integrating just a number, you just get the number times x. So it's probably easier just to remember the formula as I put it in the box there. And then similarly, the producer surplus is the difference between the upper curve, the top curve this time is the p equal p0, and the bottom curve is the supply function, so that's the top minus bottom. And again, this p sub 0 is just a number, so when you integrate the number, you just get the number times x. So rather than remembering the formula as I've given here, it's probably easier to remember it as I've given in this box over here, where the constant has already been integrated outside the integral sign. So let's tackle an actual problem. For example, suppose the demand and supply functions for a product are, the demand is P is equal to negative 0.36x plus 9, and supply function is given by P equals 0.14x plus 2. Remember, P is the price, in this case in dollars, and X is the number of units, in this case in millions of units. And we want to find the producer's the consumer and producer surpluses for this product. It's simply an application of the formulas, but in order to use the formulas, if you remember, you have to know the equilibrium point. So unless you're given it, you have to first find the equilibrium point. Well, the equilibrium point is just where the demand curve and the supply curve cross. So if you take the demand curve and supply curve and find the intersection point, you know that P is equal to negative 0.36x plus 9, and that P is equal to 0.14x plus 2. So if you take the second value in terms of x for P and plug it in for the first one, you get 0.14x plus 2 is equal to negative 0.36x plus 9. And if you add a 0.36x to both sides and subtract a 2 from both sides, you'll end up with 0.5x equals 7. And if you divide both sides by 0.5, you'll end up with x equals 14. So that's the x coordinate of the equilibrium point. Now you've got to plug that in and find P. You can plug it into either place. It should give you the same answer if you haven't made a mistake with the equilibrium point. So you can plug it in here or you can plug it in here, whichever you think is easier. I chose the bottom one. If you plug 14 in for x in the bottom one, you get 0.14 times 14 plus 2, and that comes out to 3.96. So the equilibrium point for this problem is 14, 3.96. So the first step in finding either the consumer or producer surplus is to find the equilibrium point unless it's given to you. So now we have it, and we need to find both the consumer surplus and the producer surplus. I chose to do the consumer surplus first. The formula, as we derived a minute ago, the consumer surplus is the integral from 0 to the x coordinate of the equilibrium point, the integral of the demand function, minus the product of the equilibrium price and the equilibrium quantity. Remember, we derived that formula just a minute ago. Well, the demand function was given to us, so we plugged that into the integrand, and then you've got to do P0 times X0 and subtract off. Well, this is easy. If you integrate negative 0.36x, you get an x squared over 2, but that negative 0.36 is still there. And then when you integrate 9, you get 9x. And then when you take 3.96 times 14, you get 55.44. So when you evaluate the antiderivative, you plug in the top number first. You put a 14 in there and there. And then you plug a 0 in, and you plug a 0 in there and there. And of course, plugging in zeros just gives you all zeros, so that'll be nice. So the part that you really have to concentrate on is here. So if you square 14 and multiply it by 0.18, by negative 0.18, and then you get negative 35.28, and then you're going to take 9 times 14, which comes out to be 126, and then you've got this negative 55.4 trailing. So if you do that arithmetic, you'll end up with a consumer surplus of $35.28. Not so bad. Practice using the formula, and you do need to learn the formula. And of course, now we're going to find the producer surplus. That's actually step 3. How do you do it? The formula for producer surplus is the equilibrium price times the equilibrium quantity minus the integral of the supply function from 0 to the x coordinate of the equilibrium point. Well, we know what the supply function is, so we plug that in, and we plug 3.96 in for the equilibrium price and 14 in for the equilibrium quantity, and we already know that 3.96 times 14 is going to be 55.44, so that part we don't have to do the arithmetic again. And the integrand is going to be simple as well. So you integrate 0.14x, you get 0.14x squared over 2. And when you integrate 2, you get 2x. And again, you plug 14 in first, and then you plug 0 in. And when you plug the 0 in, that whole thing's going to 0. So that makes it pretty nice. Be very careful about this minus sign sitting out there. I would actually put brackets around everything else to make sure I don't miss that sign. But when you plug 14 in here and here, you get a 14 squared here and a 14 times 2 there. 14 squared times 0.07 comes out to be 13.72, and 2 times 14 comes out to be 28. And remember, that minus sign is still sitting there, and that 55.44 is still sitting there. So when you simplify that, 13.72 plus 28, you get 41.72, and then you've got 55.44 minus 41.72 is $13.72, and that is a producer surplus. So just practice, go through this, make sure you know your formulas, make sure you can find the equilibrium points, and then practice the procedure and practice doing the arithmetic, and be careful with the signs.